introductory Monday of the academic year at this time in this room. And this is the last meeting for winter quarter, so we will see you all again in April. I don't know how that's possible, but so I'll give you a preview of upcoming talks in just a moment. But please, there's a sign-in sheet going around. If you haven't already signed it, please do. That helps us keep track of our sponsors, for our sponsors, about who attends every week. And let's see, so before I introduce today's speaker, I'll just give you a little bit of a preview. The first two speakers for next quarter are Alexandra Binder, who's here at UCLA, and then Pam Ye, also from UCLA. So that's coming, and actually the third speaker is also from UCLA. I dug deep this time. Hazel Byrne, who's a postdoc with the Institute for Society and Genetics. So we have those to look forward to. Most of the titles are not up yet for spring if you look at the website, which is at beck.ucla.edu, but we are asking people to let us know their topics ASAP, so that should be updated soon. Okay, and without further ado, I'm going to introduce, is it Raziel? Raziel Davison, who's talking to us coming from UCSB and talking about an evolutionary retrospectives on human life history. So welcome.
Thank you for inviting me. Interested to share some work with you folks that I've been doing with Michael Gervin at UC Santa Barbara in the Department of Anthropology and the Broome Center for Demography. So the title and abstract that were circulated are still relevant, but I rescheduled the talk. It was originally going to be in November, and so there's a bunch of new stuff that I've added to extend the work that we've been doing to make it even more relevant to you folks here and looking more at culture and behavior. And so the build comparative demography is going to be slightly foreshortened to make room for that. And I'm trying to take the units in this talk and trace them together to specifically court you folks by tracing the the intersections of behavioral ecology, evolutionary demography, and cumulative culture. So I'm an evolutionary demographer and a behavioral ecologist, and getting into some of the more soft culture stuff at the end of the talk, where we talk about information value and how human behavior alters human life history evolution is essentially the theme of the talk. So the motivating questions behind these studies are, one, what makes humans unique? How do human life histories differ from chimpanzees? And so to do that, we have a comparative demographic framework comparing chimpanzee and human life histories. And then we ask, how do human behavior and human life history interact? And so what features of human behavior are unique to human life histories and how they influence human life history evolution? So the operational questions going into this talk are, first of all, what are the demographic rates driving fitness differences within and between species? So this is a comparative demography decomposition of the life history drivers of species and within species differences between chimps and humans. And how does behavior, in this case we're looking at subsistence strategies, alter selection pressures? And ultimately, how can we evaluate fitness contributions after reproduction ceases? So I'm getting into some of the work that we've done has developed methods to try to estimate fitness contributions after reproduction ceases. And so at the end of this talk, I present some of those models. So this is kind of a schematic outline to the talk where I'm envisioning a path from evolutionary demography to behavioral ecology along a sort of continuum of scholarship and inquiry, beginning with a human versus chimpanzee life history comparison, where we find that there's incomplete overlap in life history envelopes and exploring some of the drivers of those differences. And then how selection pressures evidenced by sensitivities and elasticities, these demographic animals that people use that estimate the effect of vital rate differences on fitness, and then how you can use these to estimate actual fitness contributions using a method called the life table response experiment. Has a lot of traction in ecology, but has not been applied to humans. And then I'm going to get into some brief talk in qualitative terms about the post-reproductive lifespan, and then look at how human behavior can recede the shadow of selection that Hamilton and Medawar and Williams talk about, that prevents selection from favoring survival after reproduction ceases, by estimating indirect fitness contributions in post-reproductive life. And to do this, we come up with a couple measures. One we're calling productive value, which is economic analog of reproductive value that looks at the value of indirect fitness contributions via production transfers. And then at the end, I have a bit of a teaser where we're extending this even beyond surplus reproduction into old age to look at the value of information transfers and pedagogical contributions. So these two last bits are novel measures for the fitness value of surplus production and subsistence information transfers that we're working on. The first, we have preliminary results for proof of concept, and the last is a conceptual model that's still in formulation, so I don't have real outputs for it yet, but it can stimulate discussion. So to compare human and chimpanzee life histories, I'm taking an evolutionary demography lens that looks at the roles of fertility and mortality across the life cycle. But different than physical evolution, which leaves a fossil record, life history evolution is difficult to ascertain from fossils. People try to estimate mortality and fertility rates of extinct species, very difficult. Even historical data is difficult to reconstruct. But extant hominins provide clues about our evolutionary history. And so we look at extant humans and chimpanzees to find some insights about how that life history evolution could have happened and what selection pressures would drive it. So in this approach, we're looking at hunter-gatherers specifically because they're the closest to ancestral life histories, with natural fertility, subsistence foraging, and ethnobotany, but no modern medicine, driving the low mortality rates we see in modern country data. But with the caveat that these living populations are not living fossils of historical context and may differ significantly from the evolutionary background where humans evolved, but they're the best proxies we have, and so we're going to use them to make inferences. Likewise, chimpanzees are the closest we have in the primate world to our most recent common ancestor, but they have also diverged since the human-chimp split. And modern anthropogenic effects likely differ from the evolutionary context, so we also have to recognize that these snapshots of current populations are not replicas of ancient life histories, but they can give us pointers to show how they differ and what similarities it might be. So to do this, I have data that assembled with Mike Gervin on 10 small-scale societies and 5 wild chimpanzee populations. 5 of the human populations are hunter-gatherers. We're using the earliest contact or pre-contact data that's available with high quality. And then we have data on a bunch of what we're calling non-foragers, but are really foraging horticulturalists, pastoralists, and hunter-gatherers who have had contact and some acculturation and are not living the paleo life ways, but still have subsistence economy and natural fertility. And where we have collected, it appears to be all the high quality demographic data that you can find on small scale societies. There's a few that may be forthcoming, but they're disappearing in the world and there's a limited opportunity to get them. This may be our best view of what hunter-gatherers' life histories are like. And the data we have are geographically dispersed across continents, but clustered in the tropics, just by the nature of where the people were that were studied and who was left when they got to them. And so this table is kind of a broad scale comparison of human versus chimpanzee life histories, where it's clear that humans live longer than chimps, but some chimpanzees live quite long lives, as Brian Wood has shown with the Ngogo chimps, that they may, under good conditions, rival hunter-gatherer life expectancies. And some human hunter-gatherers have extremely low life expectancies. The Agta had an average lifespan of only 21 years, which is well within the chimpanzee range. Human and chimpanzee total fertility rates don't significantly differ. Human fertility is more variable, but on average, we could not find a significant difference, which was surprising to us. Survival conditioned reproduction differs greatly. That's what we call fitness, or survival discounted reproduction. Survival conditioned reproduction, which is total fertility, is what you get if you live through your childbearing years. And it shows that if a human and chimp both lived to age 50, they'd have the similar amount of children. And human fertility is more variable. Chimpanzees mature earlier, 5 to 10 years earlier than humans, and we find that jump on reproduction makes a big difference, although they have lower survivorship to maturity, so that's a counteracting feature of their life history. But we find that chimps can actually breed as early as 7 years in that captivity, and humans are also breeding at early ages in modern countries. USA, age of menarche in 2014 was 12 to 13 years. So the brackets we have on hunter-gatherers versus chimpanzees are not the same as modern country data, and so that's one of the reasons we're looking at these ancestral or traditional societies as a way to assess what human life history before the demographic transition might have looked like. Chimps don't have a significant post-reproductive life stage, but humans have a long post-reproductive life stage with surplus adult production. And that's the key feature of human behavioral ecology that we look at later to estimate the fitness contributions of production transfers. Chimps have a faster life history, and humans have a slower life history. On average, in general, chimps load their life history on the front end, and humans spread it out longer. But even within species, there are fast-slow continuums, and there's quite a diversity within humans in the fast-slow life history spectrum. Chimps are independent at 5 years old and have short childhood and long IBIs with no overlapping dependency, which is a big difference from humans that have extended child dependency, short interbirth intervals, and overlapping dependency, which makes it much more tractable for humans to try to get these inclusive benefits that we look at. And food sharing is limited among chimps. They do share some meat, but among humans, intergenerational transfers, reciprocal trade, risk buffering, and widespread sharing are fairly ubiquitous. Chimps have fairly simple subsistence with some cooperative hunting. Humans are complex. Chimps have some social learning, but without language, teaching's limited. And humans have some direct instruction, increasing skills. Some people have found things they call teaching in chimps. The Thai chimps have supposedly been shown to teach each other how to crack nuts. So it's not unique to humans, but humans it is much more common, but even in humans it's debated how much teaching there is. And there's a whole literature on whether hunter-gatherers teach much or whether it's mostly passive learning that happens. So we're looking at teaching in kind of we're black boxing the mechanism about whether it's how the learning happens. We're just assuming that teaching is anything that increases your knowledge or your skill, but that it also entails some cost to the teacher in terms of reduced production in this case, if they're teaching you how to do subsistence activities. So if we switch now to look at the selection pressures and fitness contributions of these within and between species differences and ask what is driving the differences and how much variation is due to each given vital rate. That's what these life table response experiments I'm about to show you do. They take the population level fitness of one versus another population, maybe one's growing, one's shrinking, and they say how much of that is due to fertility or mortality at different ages. So I'm going to use this method that is widespread in ecology, especially conservation biology, to look at what's driving species level differences between humans and chimps. And then ask, what do these vital rate contributions tell us about human life history evolution, if we can gain any insights from those differences. So life table response experiments started in the 50s, looking essentially at environmental toxicity effects, and have been applied in a lot of experimental contexts to look at treatment effects, but they also are used in natural experiments and conservation biology, trying to figure out what's driving population level differences. And these are the sources that are used. Caswell's 2001 book has a whole chapter on it that makes it really easy to figure out how to apply it to your particular system. There's lots of different approaches. We're using a very simple mean rate difference fixed treatment experimental approach. So essentially it breaks the population growth rate down into these contributions. By comparing each population, we'll call a population N, to some common reference R. In this case, we're using the mean chimpanzee life history as being the referent, but you can use anything as long as you know what you're comparing and that that's what the point of comparison is. You can then compare the deviations among different groups to see how they differ, which is what we do for the within species. So these contributions, C, add up to the total difference in the population growth rate. And they are, each contribution is the product of the sensitivity of a population growth vital rate and the difference between populations in that vital rate. And the sensitivity is essentially the slope of fitness with respect to that vital rate, which could be fertility or mortality. And the difference is the difference in that vital rate. These AIJs are the matrix elements I'm about to get to, but that could be a fertility or mortality rate at any age that could differ, and then the sensitivity scales that to get the fitness effect. So these are assembled in a matrix model. This is a classic Leslie matrix that has survival, px, on the subdiagonal, the chance of going to be 1 year older in the next year. And then fertility is the chance of producing 0-year-olds at any age is in the top row. The rest is 0, and this matrix summarizes the entire life history of a population. And this is what we use to calculate these measures and compare them. So if we look at mortality and fertility of humans and chimps, this is the mean plus or minus 2 standard errors of the mortality and fertility of chimps versus the humans in our data set. And we can see that there is some overlap in early life, but that there's minimal overlap in mortality, and chimps generally don't live past 50, 55 years old, whereas humans have a long post-reproductive lifespan. Whereas fertility is much more overlap. Chimps start earlier and end later, but in the prime years, fertility is very similar. And if chimps and humans survive to those years, their life course in that period is also similar. Oh, sorry, I said that. So chimps begin earlier and later, similar prime age fertility. So if we look then at the sensitivity component of these models, it's essentially the slope of fitness, lambda, the population growth rate on the y-axis, and the difference in the vital rate on the x-axis. And if you toggle a vital rate higher or lower, this is the effect on fitness of that vital rate. And if sensitivity is lower, you get a smaller slope and less effect for any given difference in vital rate. And to compare these, it's convenient to look at these things they call elasticities, which is a proportional effect on fitness of a proportional change in the vital rate. It's essentially just scaling the sensitivity by the population growth rate and the mean of that rate, so you can now have a bunch of values to add to unity. So essentially the elasticity then is the percent of the total difference, the percent of the population growth rate potential that is due to a vital rate. And then that goes into the difference when we put it in the life table response experiment. So elasticities reflect the force of selection on vital rates. And they're often used in a prospective manner to say what you'd expect selection to say about a life history. And they generally find that selection on juvenile survival is high. This is constant across most animals and certainly among humans and chimps. The most important thing to have a population survive is to have the juveniles survive. But that doesn't mean that that's the biggest difference between populations, because you have to scale it by the observed difference. So people use these prospective measures to make predictions about life history, but it requires you actually look at conditions on the ground and retrospectively decompose them to find out what's actually driving dynamics. And after reproduction begins, selection drops due to mortality attrition, because the fewer individuals there are at each age, the less selection cares about whether your kids survive or whether you have kids or whether you survive an additional year. Selection on early survival is higher among chimps, and selection on late survival is higher among humans, and that essentially reflects their differences in mortality. After the humans begin reproducing, selection is higher on human survival. For fertility, obviously selection's higher on chimp fertility earlier because humans aren't reproducing yet, but it's similar in prime years, although humans have slightly higher fertility elasticities. And that goes into how much bang for the buck a fertility difference gives you when you compare populations. So essentially these elasticities and sensitivities are the bang for your buck you get when you change a vital rate in terms of the fitness consequence. And if you add all the bangs attached to all the bucks, you get the total account of the difference in the population growth rate. So it's a retrospective decomposition of the difference. So to do this, you have now on the y-axis either one of these three objects, an elasticity, difference in the red. So that's here survival of humans minus survival of chimps. So everywhere the red line is above 0, humans survive more, and everywhere it's below 0, chimps survive more. And elasticities we just looked at are the bang for your buck out of that. That's high early, low late. And then the contribution is the product of these two. And so that's what we look at in this comparison, is how the contributions differ between the vital rates. And what we find is that comparing humans and chimps, 5 out of the 10 human societies we had higher infant mortality, neonate, age 0 to 1 mortality, than the mean chimpanzee mortality rate, which was very surprising. So that means that, in essence, human infant mortality or neonate mortality is hurting population fitness relative to chimps. And so it's the one negative contribution of survival in this case. And it has a very high elasticity, so it makes a pretty good contribution. Child survival has high elasticity, but the difference is positive, so child survival increases human fitness relative to chimps. And adult survival is also higher, and although the elasticities decline, I can't see it, the elasticities decline across this period, it's a big part of life, and this has a large effect on population differences. Whereas late life, there's no fertility, survival doesn't matter, there's 0 contributions, direct contributions to fitness. After human menopause, and chimp's lifespan is about the same time. So after age 50, there's basically no play. And we get at that later when we're looking at post-reproductive contributions. So doing the same thing for fertility, we can see that early fertility is lower in humans, and that has a pretty large negative effect for human fitness versus chimps. Essentially, chimps get a jump on fertility, and that gives them an edge. But humans have higher prime age fertility between ages 20 and 40, which allows them to have a net positive difference with the chimps. And then in in late life, again, chimps are reproducing more, but elasticities are so low in late life fertility that it doesn't make much difference in terms of population growth, right? And again, beyond age 50, the shadow of selection prevents these elasticities from making contributions that show up in an LTRE because there's zero sensitivity to those rates. So if we summarize the life history differences, we can add the contributions of different vital rates across age ranges. And so this figure here has the hunter-gatherer mean life history versus the chimps. And on the y-axis are the contributions summed across different life history transition types. And for comparison, I'm separating negative and positive contributions. So the negative contributions are below this line 0. The positive contributions are above. The white line is the net contribution. When you add all the positive and negative contributions, that is 0.275 or what? 0.0275 is the difference in population growth between mean human hunter-gatherers and mean chimps. And then this black dot is the actual population growth rate, just for reference. So then we can look at how each of these parts of the life history affect the total difference in population fitness. Positive contributions increase, negative contributions decrease. Oh, and they net, and then this is the actual population growth rate. They add to reconstruct the population growth rate. As long as there's not a lot of density dependence or stochastic influences, they're pretty good at replicating population growth, and the standard error in these populations was 10 to the negative 4 or something. So it does actually reproduce the population growth rate fairly accurately. So if we look at these details, we find that, as I said before, neonate survival is a negative influence in humans, but infant survival is a little bit higher. So that counteracts the negative effect of infant survival if we do 0 to 2 as a bracket. So that still has a net negative impact of infant survival. Child survival is positive. Adult survival is positive. And after age 50, we have no survival or contributions of fertility, but as a reminder that even though chimps don't live beyond that and humans don't reproduce beyond that, humans do live to that age. And in hunter-gatherers, 29% on average live to age 50, and they have almost 5 years of life left to continue contributing indirectly to fitness if there's an opportunity to do that. Early fertility is quite a bit lower in humans, and this is that chimps getting the jump on reproduction that lowers human population growth relative to chimps. Prime age fertility is positive. It increases population growth, and this is like a catch-up that humans do relative to chimps in midlife. And late life fertility, because so few chimps live to those ages and so few humans are reproducing at those ages, there's not much of an effect of late life fertility after age 40. So most of the fertility action is negative early and positive prime fertility affects humans versus chimps. And zero fertility contributions after age 50. But again, they're living that long at high rates. So if this is a within human comparison to show how there is within human variation, this is the two groups I'm comparing: the hunter-gatherers, the 5 hunter-gatherers versus the 5 other small-scale societies, to see how horticulture and production, and as opposed to strict foraging, might make a difference in life histories. And we find that among the hunter-gatherers in our group, infant survival is higher, and that among the non-foragers in our group, they don't have the negative effects of infant survival, and so that doesn't lower their population growth relative to chimps, and they have much higher population growth rates. Child survival is about the same effect as in hunter-gatherers, but adult survival is more. They have lower adult mortality, and that makes a big difference in how many of those prime age fertility contributions are made. Early fertility is similar, but a little bit lower in hunter-gatherers, but prime age fertility is a little higher in hunter-gatherers. So hunter-gatherers start later but have higher prime fertility and catch up a little bit, but they don't have as high fertility or as high population growth rate. And that's essentially showing us that more complex subsistence lifestyles, including horticulture, allow rapid population growth, niche expansion, and these populations are growing at faster rates, but it's hard to say how much of that has to do with the particular circumstances. A lot of these populations are recovering post-contact or have transient dynamics that may increase their population growth rate relative to what we'd expect over evolutionary time. So again, there's the caveat that we have snapshots, but that's the best we can have about these populations to say what might be different in terms of how subsistence affects life history. Late fertility is similarly low among both these groups. So if we take these contributions and we likewise scale them the way we do with elasticity, so the magnitude sum to 1, and so the opposing forces of positive and negative contributions are given equal weight to see how much traction each vital rate has on population growth, we can see that infant survival effects are similar magnitude across humans. They're just negative in hunter-gatherers and positive in the other groups. And child survival effects are similar but both positive. So child survival isn't much different. Infant survival is a lot different, but then adult survival effects are less important to hunter-gatherers, more important to non-foragers. Early fertility effects are slightly more important to hunter-gatherers, but this prime fertility effect of hunter-gatherers is a really big difference between human groups, is the higher fertility in later life of hunter-gatherers, whereas a lot of the forager horticulturists have a lot of reproduction early and then waning. So if we summarize the difference between humans and chimps, adult mortality and fertility are stronger drivers than child mortality, which was it's a surprise to me. I'm not an experienced primatologist. I thought child mortality was going to be the big driver, and it turns out it's adult mortality. And also that human and chimpanzee fertility are similar, but mortality attrition limits chimpanzee fertility, which does not appear well appreciated. Even in the paper where we got the chimp fertility data from, they did not highlight this fact that survival condition fertility is so similar, because mortality effects are so strong that life histories are different. Another big difference in humans that I didn't get into in the model here, but it shows up in the effects from subsistence, is that humans have much shorter IBIs, and that this tight birth spacing is made possible by transitional foods and alloparental care, production transfers, and dependency. And also that humans have long post-reproductive lives with in-kind support, but they also have surplus production that they transfer and valuable information that has fitness relevance. So this gets us to the question of why humans have post-reproductive lifespan, which is a big field in behavioral ecology. And there's only humans among all primates have menopause. There are 2 beaked whale species that have it. They also have really long lives and a lot of culture and transmission, and Mike Gervin I'm working with is interested in how that might happen. We have some data on orcas, kin structure and foraging behavior. We might look at that as a comparison. But a bunch of hypotheses have been presented, some non-adaptive, saying that menopause just happens because we live a long time, we ran out of eggs, or that grandmothers are switching to daughters' fertility and grand offspring survival, or that male fertility, late life, and sex differences at marriage drive post-reproductive lifespans in women as a kind of a piggyback, or that absent fathers, whether they're dead or abandoned, lower selection on fertility, which further benefits you switching to helping your children's fertility instead of trying to have your own kids. And adaptive onset theories saying that timing is relative to your probability of surviving to adulthood. And so all of these go at the question of why we live a long time, but they're difficult to quantify, right? We know that grandmothers and kin, but grandmothers especially, have a lot of positive influences on their daughter's fertility and the offspring of their daughter's survival. And that also fathers can make positive contributions, and grandfathers too. They make contributions to the uptake of their children, not just in food transfers, but also in teaching. And so that gets to the question of how do you quantify this stuff? If fitness contributions are being made after reproduction ceases, there's zero elasticity, how do you get a visible effect out of a demographic behavioral ecology model? And so that's what the rest of this talk is trying to present some methods that estimate fitness effects accruing to in-kind support, which we're not dealing with directly because that's difficult to quantify, but specifically of production transfers and information transfers. Humans' reproductive value and chimps' reproductive value are shown here, and essentially that's how much future survival discounted reproduction you expect from an individual alive at any given age. And this graph shows, based on the data in our data set, that chimps' reproductive value exceeds humans before age 40, even though humans are almost done having babies, chimps are still having babies. And so this doesn't really explain why humans live a long time after having stopped reproduction and chimps don't. So there's some missing feature here that we're trying to get at. Despite a short lifespan, chimps have higher reproductive values at advanced ages. And this is a consequence of much of the human lifespan is lived in this shadow of selection, that there's zero fitness sensitivity to your survival and reproduction, so you have no way to contribute to population fitness without indirect effects that we're trying to estimate here. And the potential for these effects is pretty large. This is a graph that shows for the Ache and for the Kung at each age of a woman how many children and grandchildren. Mike made this graph. I think the grandchildren are half because it's the Hamiltonian relatedness coefficient. But essentially, how many dependent offspring do you have in your sharing kin network that would benefit from you providing for them? And that the potential fitness benefits peak right around the modal age of death. So there's a lot going on in that period of time that if you lived longer, you might have an opportunity to make big effects. So this is the question, is can living a little bit longer make fitness relevant positive contributions that then selection would favor? This is a graph showing a meta-analysis of 17 studies that showed a significant effect for maternal grandparents. So this is kind of a presence-absence natural experiment where they said if you have the presence of this kin group or not, what's the statistical effect on the grandchild survival? And it's essentially showing that maternal grandmothers and grandfathers have a positive effect. Paternal grandparents may not be so much, but all these effects are they're quantitative in the effect on fitness, but they're qualitative on the mechanism. They're basically saying that there is some effect. And so we're looking at what you can quantify about those effects, and these in-kind contributions are very difficult to quantify. Like how much fitness effect you get out of the additional survival of some kid because you were dandling them on your knee while their mom was out getting food that they needed is really difficult to do. And we're trying to find out how much fitness that food would give you, so that if you could figure out how much time she has to go spend getting food, then you could find out what that effect would be. there are mixed effects. This is another meta-analysis, but it essentially showed that mothers, especially maternal grandmothers and older siblings, have positive effects on survival. So these qualitative results make us want to quantify these effects, but for in-kind transfers that's difficult, so we're looking at it in a purely economic framework of just production effects, with the idea that there are going to be additional effects of in-kind support. It is widespread that old individuals provide substantial assistance with fitness benefits. If there's conflicts, if there's crop failures, if somebody gets sick, people come and help you, and it doesn't show here. A lot of them are old people. So 40 to 59 is high, but 60 is also very high. So these are contributions that are being made that help somebody that are some old person's effect, that shows that there's likely a large room for their ability to provide those effects. So then this gets to the part where I'm actually trying to show you the math that estimates this, the indirect fitness contribution of production transfers. If we know that production and consumption are quantifiable, food sharing is ubiquitous, post-reproductive transfers provide valuable nutrition, then we can assume that if we're near food insecurity and we're at equilibrium, having as many babies as we can with the amount of subsistence support we have, then vital weights will respond to food availability, and then increases in survival and fertility from food transfer effects could reflect in fitness contributions. So this is kind of a mean forager cartoon model of production and consumption that we're going to, after we fine tune it, we're going to apply to the data that Mike Gervin has for the Chimpanzee in Bolivia. But for now, this is a schematic kind of a cartoon model for mean forager production and consumption to show proof of concept. So for males, there's fairly early independence relative to females, but late relative to chimps. They're dependent till almost 20, but they have surplus production till almost 60. Women often don't have surplus until later in life because they're busy taking care of kids or something, but they do provide a lot of surplus later in life, and their production often extends into old age further than male production. But they may not produce as much during childbearing. In this model, I'm not doing a sex-specific model, but the ramification that we envision has a two-sex model with different subsistence activities that you can allocate time to see how time allocation and role specialization could go into this process. And females in a lot of foraging societies are producing surpluses well into their old age. 20 years after they stop having kids, they're still bringing home more food than they eat. Horticulturalists are self-sufficient just as early, and they're often productive throughout life. And in the Chimpanzee, they essentially don't have many elder dependents. That they may not be doing all the specifics of getting the food, but they're actively engaged in food production all the way into life. And so that allows them to make these contributions. So the essence of the model is that we start with an empirically derived caloric need profile, right? Mike has studied these folks in Bolivia for a long time and has a lot of data on how much food they need. So that's essentially the baseline that we tack everything to, is the minimum caloric requirement of individuals at each age. And then we take our stylized production function and we scale it so that at the survival discounted age structure of the population, total consumption equals total contribution. So essentially, there's individuals at each age who are producing and consuming. If you add up all the production across all the ages of individuals that are alive at each age and all the consumption alive at each age, they equal, so that essentially this is a functioning subsistence, that the ends meet and that the food needs are met by the contributions, but that they're in fragile equilibrium. So any perturbation will provide food scarcity, right? And then we scale individual production and individual consumption to be what you would do at each age if you were alive to get the survival conditioned production functions. Because we're scaling it at the survival discounted level where it's reflecting the age structure, how many people are actually alive at those ages to produce the food, if this is what an individual would do in their life if they survived all those years. And then the individual need is what an actual individual who's alive at that age gets in terms of food, and we compare that to what they need to figure out how starving they are, right? This quantity E sub x was developed in a project for the Hawaii Islands where they're looking at subsistence economy, and essentially it's a ratio to how much you need that you're getting that we can use to put into this function for vital rates. And then we can calculate the net at the population level of the consumption and demand, which reflects transfers, and the net at the individual level, which reflects dependency at each age, whether you're producing enough to feed yourself. The bugbear in all of this, and essentially the part that makes it work or not and is very difficult to tack down, is the starvation response of vital rates to nutrition. To actually get this, you'd have to starve people at all these different levels for all these different time periods and then watch large groups of them die, right? It's impossible to do. So the best data we have for this are natural experiments of famines and conflict situations that show there are effects, but other than that this shape is concave, there's little agreement and is not a well-characterized function. So it's concave in the sense that it curves down, right? A little bit of deprivation doesn't have much of effect, but as you add more and more deprivation, as you get further and further into starvation, the effects get stronger. But how concave it is an open question, and so we model that as a variable to see how that affects. We look at different functions of starvation to see how that would affect the predictions. So then the fitness effects of transfers depend on the nutritional effects. And so we can take the sensitivity framework we did in a life history response experiment and plug in new rates. In this case, it's the contribution of production instead of a vital rate. And then the fitness contributions feed through the vital rates. So in this model, the delta lambda delta p is the change in lambda population growth as a function of the change in the production. So this is the force of selection on surplus production transfers. It's essentially the sensitivity to food production in the population, if you can estimate all these other parameters. The vital rate sensitivity is the bang for the buck you get if you change fertility or mortality at any given age. And then this delta A, delta E is the starvation response that I just showed you that we're modeling different functions for. But that is the effect on the vital rate of the food. And then this last bit is the food ratio, which is the effect of production on how much food you get. We're assuming equal sharing in the baseline conditions, so essentially you get the proportion. If 1,000 calories is taken out of the total population budget, you just divide that equally by demand at each age. So essentially everybody's getting the same proportional hit. We're doing other assumptions where you don't give kids any decrement and you only making adults suffer, because that will have protective effects. But this is maybe not as conservative, but it will show that there's an effect, and that if you reduce transfers, then you're going to reduce fitness as the outcome. And if you add the actual rate of surplus production at age X then you can get this total delta lambda delta p, which is the actual fitness contribution of surplus production. So it's essentially the marginal fitness value of surplus production at some age. If that age all of a sudden retired or went on vacation or stopped producing food, got sick for a year, then all of that food would be missing, and then this would be the effect on fitness of losing that production. And so we can add these together to find out what the fitness contributions would be. And these are the fitness effects on the y-axis. That first we'll look at the direct contributions of survival, which is essentially the survival times the sensitivity to find out how much of population growth is due to survival. And then there's the fertility contributions, which is smaller, that shows how much is due to fertility. And so these two, the fertility and survival contributions, add up to the population fitness. So this green line is essentially how much of population fitness is reflected in the contributions at each of these ages. And then this black line, which you can't see here, is the surplus production contribution. Right? So this is the effect on fitness of the reduced production at that age. And although it's small in this graph, you can see it affects through fertility and mortality, right? So it's an indirect effect that has direct effects through the changes in fertility and mortality. And it continues after reproduction ceases. That's the key feature of this, these are contributions that happen after age 50. And assuming relatively strong starvation effects, we can get shapes of these that show that depending on how strong starvation is, or starvation effects are, that they could rival fertility contributions. If survival is one of these black lines, these three black lines I modeled are the shape. So if here at 40% consumption, you have 80% of baseline survival, essentially. Whereas if the starvation function is not as strong, then you have 85%. So it depends on which of these lines you are where you end up, but a lot of these lines end you up in a place where these fertility contributions add up. So then the question is, how often does this actually happen, and when do production contributions make big enough differences that selection would matter? And so what we're showing is that you can estimate that with these survival functions if you have some assumptions built in about the survival. They may rival direct fertility contributions, but the effects also differ in their contributions through survival versus fertility. And because fertility effects are so much smaller, the dotted line is the survival without the fertility, and the solid lines are fertility. So essentially showing that if effects are on fertility rather than survival, you need a much stronger effect to have the same difference in population fitness. But that's what we find. In the literature, they say the fertility suffers before survival, that often fertility will drop to zero, and you just wait out the famine, and then you start reproducing again. Whereas if you die, you're never going to reproduce again. So that's why survival effects are so strong. And again, this is all happening across the life stages in post-reproductive period. So this allows indirect fitness contributions. So we've shown kind of schematically and with some assumptions, arm-wavy, that if you can characterize the fitness effects of nutrition and the production transfers of old people, then you can estimate the fitness effects of old people's production transfers, and that should extend selection past menopause. Longevity often exceeds surplus production, though. So we have individuals who are not producing, they're elder dependents. So what value do they have that selection could look at? And elders possess valuable ecological knowledge and fitness relevant skills, so knowledge transfer may allow indirect fitness contributions. So here we're extending selection even beyond productive surplus years to ages where individuals are dependent but can make positive contributions to fitness via information transfers. So this gets us to this last animal that we're trying to estimate, instructive value, which is essentially the value of an individual at some age through their indirect fitness contributions that they have through pedagogy. In this case, we're looking at direct fitness-related pedagogy, but you could look at other ways of sharing culture and knowledge that have fitness effect, but we're funneling all of our effects through production, so it's fairly conservative. Only the effects that influence how much you produce are going to make a difference in this model. So the questions are, what fitness contributions are made by dependent elders? How do we evaluate the fitness value of information transfers? And one question we're wondering is a paper that you did with the birds looking at how cooperative foragers often, the ones who are most successful come back with a bunch of food and then they share it and their family doesn't necessarily get more. So the question is, why would you keep sharing if you're not going to get more? And a bunch of good reasons are presented for it. You might get alliances, you might improve your relations, increase cooperation, different social effects. But we're positing that there may be information transfers going on in cooperative foraging that can hurt a successful forager's production, but that benefit the pupil in that relationship, that will increase future production, that then can be shared in the community to offset some of the costs to the more productive foragers in that case. And then we're wondering how this can be seen in a coherent framework of community culture where pedagogy is a way to transmit valuable ecological information across generations, and that the fitness benefits of having old people is significant. So post-reproductive adults are often cultural experts and educators, and sociality is fundamental. There's a long, low production period of childhood where individuals are dependent and they're assumed to be learning skills. So if they can learn them faster, they'll be more productive later. And elders are repositories of ecological and cultural knowledge. They've been around a long time. They know where the food is when it's scarce or when it's dry, where to go for water. They have a lot of information that if they die with it without giving it to somebody, then the population might not do as well. And the underlying assumption here is that teaching may be adaptive, that it fosters cumulative culture by increasing knowledge transfers, allows for earlier skills mastery, increases production in the sharing unit, and that the fitness contributions of pedagogy can feed through pupils' productive value to increase population fitness. So this question has been looked at quite a bit of whether there's teaching, and there's whole books on whether or not hunter-gatherers teach. And there's a bit of a debate. Some say no, some say yes. It depends maybe on how you define teaching. We're defining teaching as anything that improves your pupil's outcome. So it doesn't have to be direct tutelage necessarily. And this picture, without getting into details, basically shows ages at acquisition in the green and ages at mastery on the right, and shows that individuals get a skill way before they're really good at it, and that having people who are old and really good at skills can help people learn those skills faster, essentially. And that the highest skilled individuals are often past prime production, and some of that transmission might be non-subsistence related, might be oral traditions or storytelling that is even not addressed in this model. So although we're making assumptions about starvation effects that drive the indirect effects of production, there are also indirect effects of in-kind transfers that we're not estimating that make our estimates a little bit more conservative. And again, to remind you that there are a lot of kin around to benefit from having older people around. So I'll try to go through this really quick. Essentially, the model framework assumes that production depends on strength and skill. Strength increases early but declines early. Knowledge increases slower but doesn't decline as early. So old people are weak but knowledgeable. Young people are strong but inexperienced. So strength peaks at a much earlier age than skill. And so this is a stylized model. You can change the shapes of these, but the qualitative prediction should flow. And so production is a joint function of strength and skill. Depending on the strength and skill requirements of any activity, you can weight those into a joint function that gives you production at each age, depending on your strength and skill at those ages. And that's going to peak at some intermediate age when you are strong but also skilled. And so we're looking at population growth response to knowledge transfers with this animal now, which is an extension of the previous one. And this is the force of selection on pedagogical time allocation. And the core of the model is the same exact productive value approach. It's just we're adding indirect contributions of information transfers. There's the DP, DK. K is skill in this case. So that's essentially the skills impact on production. How skills intensive is that production activity? And then this important parameter here, DK, DT, which is how skills acquisition responds to teaching. Essentially, how much faster do you learn something if you have a teacher versus not having a teacher? And we ask with this model, what conditions would favor pedagogy so that future gains of production exceed current costs? And then what are optimal pedagogy schedules? What ages of teacher and pupil should be paired to maximize group production? And then how do high and low skill activities or kinship and sharing networks alter our predictions to get more nuances out of this? So that's kind of a dangler teaser. This is what we're working on now. We're trying to get these results where we have essentially shown that teaching, as you'd expect, you want an old teacher and a young pupil, because you want the pupil as early as possible to have as much downstream learning benefits, and you want an old teacher who's skilled but isn't producing much, so there's a low cost to their production. And the optimal pairing and the duration of instruction all depend on the boost to the pupil's learning, the cost to the teacher's production, and the skills intensivity of the activity. So if we can get all that estimated, which we do in our model except for the arm wavy survival function, we can do the same thing we did with production and look at what's the marginal impact of pedagogical transfers. Essentially, it's the time allocation to teaching at a given age and how much is that going to affect fitness, to see how selection would favor longevity even post-productive surplus. So to sum it all up, I kind of made this table comparing the fitness value of individuals estimated by classic reproductive value, which just shows direct fitness contributions that are the genetic success of an individual, but that we're presenting productive value that shows the economic contributions through nutrition, and instructive value, which shows pedagogical contributions through skills transfer. And to sum up, essentially we found that human-chimp differences are mostly due to adult survival, despite similar fertility, that age at maturity and inner birth intervals play a large role, and because humans have menopause doesn't actually make much difference in human life histories because humans stop reproducing, but the chimps are all dead. And among humans, infant and adult survival makes a big difference, and early versus prime fertility in hunter-gatherers versus other foraging groups. And we also showed that indirect fitness contributions extend selection beyond reproduction via production transfers and also via knowledge transfers. And so they push back the shadow of selection to allow evolution to care about survival post-reproduction. And the take-home point that I am trying to frame this all in a coherent feedback between behavior and life history evolution. Essentially that in the gene by environment interaction, that there's a key component missing, which is behavior. And that instead of a GBE interaction, I'm proposing there's a GB interaction, and that behavior can actually affect your life history, and that your life history affects what behaviors you should do. So there's a feedback between behavior and life history that often doesn't show up if you don't look at these indirect effects. So thank you for your attention, and I'd like to acknowledge Tom Kraft, my lab mate at UCSB, Shripad Toljapakar, my advisor at Stanford, Cedric Pulston at Davis, and Oscar Berger at UT Austin, who all looked at previous drafts of this. So sorry, I apologize, a bit of a whirlwind. I was trying to extend it really into the culture bit after having already committed to the comparative demography bit, but I hope that it threaded through enough that you felt like it was coherent.
In the comparative demography part, the humans, in my understanding, have a relatively high maternal mortality rate at delivery. One of the major causes of early death.
Big heads of babies and upright bipedalism,
years.
right? Yeah.
And not only the mother dies, but the infant doesn't survive, and her dependent children don't either. And yet when you talk about, in the models, you talk about the age you were when you had the last kid. And shouldn't you be talking about the age you are when the last kid is truly independent of your care, like 15 years later?
Well, that is what a lot of people say, that fertility is to replace you, right? And that a lot of life history theory says that if there's higher mortality and your kids are going to die more, then you have more kids. So how many kids you have that survive to adulthood is what you really care about. And so what was the question?
I guess it's just, it seemed like the model, looking at the chimps versus the humans, wasn't taking into effect the fact that you have to live at least 15 years past your last kid.
Right, so that would then...
To someone who can fledge them in 2 weeks.
Right. Well, what we're looking at is just the direct effects of fertility and mortality. Mm-hmm. So essentially the effect of fertility happens once when you have a baby. Mm-hmm. But the effect of having a baby percolates downstream in that baby's life to survive the reproduction, right? And so the sensitivities are supposed to account for that in terms of if you survive to age X, then you're likely to survive the rest, and so your sensitivity reflects your likelihood to survive in future life. And so it doesn't reflect your likelihood of surviving till your kids. So that you'd have to take into effect, essentially quantify those kinship relationships of how likely you are to die depending on whether your parents are alive at each given age, which you maybe could do, and that's what these people have done statistically. What we're looking at is what mechanisms you could impute that would do that, and if production transfers are one of them, then you could look at the actual effects of the production at those ages that feed through the survival. So then if an individual died and you'd lose their production, then that would affect the survival of their offspring or whatever. Did I answer the question?
Yeah, it's all complicated.
Sorry.
I think following on that, I think you're already factoring on survival to the age of reproduction if you're counting the fact that to have a birth you have to have survived to that age. So if you were adding the chance that you survive to your offspring, so you would be counting that twice in a way, unless you think there's any difference between survival of mothers and daughters, but I'm thinking in my history you do. So I think this is already factored in by the fact that the person has to survive to the age of first birth or something.
Well, it doesn't get at the heterogeneity in the whether you are orphaned or not. So these demographic models average across all the individuals at every age, and so it assumes that on average you're likely to be orphaned some percent, and so some percent of people are orphaned at that age. So it doesn't get at that latent heterogeneity, which you'd have to build dependencies on kin structure or some mechanism that would affect the outcome.
Well, I also had a question, so I was just asking. Didn't get where you the data you got from on the effect of nutrition on fertility, because I know there's a little controversy over that. So you mentioned you use historical famines to try to estimate the survival curve and convexity, the concavity of thereof. Where did you get the data on fertility, nutrition effect on fertility?
Well, what we have in the model is not data. It's an imputed function that we're using that concavity parameter as a variable. So what all the papers that we see out there that look at starvation effects on fertility or mortality have concave function. But they all have a different shape, and they're all looking at different degrees of starvation for different periods of time under different ecological conditions. So to get that actual shape would be very difficult.
So sorry to follow that. So you estimated like a maximum likely data coefficient based on what you actually...
No, it's not. It's essentially saying we don't know what the shape of starvation is. It could be stronger or weaker, and we're just varying that parameter that is the strength of starvation.
So, first, I'm way outside my area here, so forgive me if I'm misunderstanding or that remark is naive, but it seems to me, given the key finding that adult mortality is where the rubber hits the road in terms of differences in the vital rate, that your knowledge transfer models are, you're focusing on incremental knowledge transfer, and incremental knowledge transfer will affect overall economic productivity, and for that reason, your argument that it's best to have, an old repository of knowledge and a young learner, because the young learner will get maximal return on the knowledge transfer over an economic career. That makes perfect sense. But both with regard to starvation and other important fitness impacting events, it may be that the critical knowledge transfer is not actually the incremental increase in expertise in quotidian subsistence activities. Not that that doesn't matter, but it may not be one of the critical features. The critical feature may be knowledge relevant to rare events, right? So, and in particular, your use of starvation is illustrative of this, and that starvation, while the challenges of subsistence are there all the time, starvation is generally a rare event, right? Similarly, dramatic shortages of one kind or another, natural disasters, diseases, or even things that are affecting only individuals and not populations, like illness or injury, right? Those may be relatively rare events, and having an elderly repository of expertise that addresses those events is now independent of the age of the learner, right? That the entire lineage benefits if that individual knows what to do with
That would be
this
some kind of in-kind transfer that wouldn't go into the production function.
Yeah, it doesn't go into production.
Yeah, so
function at all.
that is an additional value that they'd have. We're just looking at essentially the skills effects.
I understand. My point is that and forgive me if I haven't articulated clearly, that your application in that regard is not taking seriously enough your own prior findings that adult mortality is where the rubber hits the road. Because if you take that seriously, then incremental differences in production on a typical daily, weekly, monthly, or annual cycle, those make small contributions to mortality, because most of the time individuals aren't dying because today they didn't bring home the bacon, right? Most of the time those individuals are dying because of illness,
right,
injury, or rare dramatic events like famine.
We're modeling this at the annual round. So it's not a daily activity schedule. We're saying annual production across the entire age.
What I said still holds exactly true, right? In that adults don't die because of incremental differences in their economic productivity. Adults die because of rare events. Those rare
Adults
events-
die for all different reasons, and they may die because they get infection that they're more susceptible to because they didn't have enough to eat for the last few weeks.
Possibly, but that infection is itself a punctuated event, is my point. And that
Sure.
having
Most
healer
mortality
knows
is.
what to do
Yeah.
in those events, right?
Yeah.
So that is, the return doesn't necessarily, it's not, in that set of circumstances, the return is not contingent on the age of the learner in the same way.
Right. Yeah. Well, if you have other avenues to affect fitness, then they wouldn't. We're looking at the age of teacher and learner because we're looking at the skills and production profiles across age. And essentially, if teachers increase the skills acquisition rate, then that would have downstream effects.
Yeah, I would just, again, and I'll stop perseverating on this, encourage, and Mike's the expert here, so maybe tap his knowledge of the ethnographies. But my guess is that elderly people they're not going out hunting and showing, young adolescent boys what the best techniques are. They're too old for that, right? So they might be imparting some, quotidian economic subsistence relevant information, but a lot of what they're doing is probably, oh, here's a rare circumstance that no one has encountered before, and here's how you address it.
Sure. Yeah.
Because it's the prime age producers who are teaching within both your, stylized model definition and probably the observable behavior on the ground.
Yeah.
right?
Thanks. We'll look into that. I think that if we can get more of those indirect effects included, that it essentially increases the traction that old people have. So, yeah.
Great talk, Raz. This is really pushing the modeling of economic productivity into the biodemography to its frontiers. So it's really fantastic work. And my question is a little bit based on your experience having looked at the predictive value of a sensitivity analysis to be able to prospectively predict what actually occurs in changing environmental situations. So for example, when you looked at the comparison of sensitivity of fitness on mortality, in a standard mammal model, of course also humans and chimps included, you see that survivorship at young ages has the biggest impact on length. But when you actually see a case of, when you do the comparison of humans to chimps, and you see that the organism doesn't function that way, it doesn't respond that way. We see and your life table response experiment demonstrates that in the clearest possible way, that we see the actual contribution demographically is adult survivorship and other variables, but that's the main one. So my question is, given that linkage between the observed outcome and what a standard sensitivity analysis would suggest would be a leading cause of fitness differences, how do you approach your modeling of the elasticities on storytelling, the elasticities on food production?
Right, because they don't include that difference term. Right.
Well, yeah, and
There's no scalar.
When you see the empirical data in light of the models of population growth differences in humans and chimps, and it doesn't correspond to your predictions, or it doesn't correspond to the simple mapping on of the sensitivity of population growth to mortality. What are you looking for in your model of the fitness contributions of production and skill transfer? If your model predicts, for example, that you have a high fitness impact of food production at age 40, 50, 60, 70, okay, is this modeling exercise meant to provide a highly plausible account of human life history evolution?
That would depend
Or
on
is
that
this-
production value, right? Because the sensitivity is multiplied by the production to get the effect.
Yeah.
So if production's high and sensitivity is high, then you get a big effect.
Well, yes, within the bounds of your model. Okay, certainly.
In demography, have you heard of there's this thing called the buffering hypothesis. Kathy Pfister presented in 98. Essentially, across all these different species they're looking at, although not in every case, in a lot of cases, there's a negative correlation between the variability of a rate and the selection on that rate.
Yeah.
Essentially, that natural selection acts to canalize important vital rates. That if a vital rate has a high elasticity, there's going to be strong selection balancing that rate to not be variable because variability is negative.
Yes.
But if that happens, then high sensitivity rates are going to have low differences.
Yes.
And there's a paper to 2000 that shows exactly that
Yeah.
that sensitivities are often not the ones making the difference because they've been canalized,
Yes.
and that the ones making the difference are a completely different set of rates that widely differ,
Yes.
even if they have smaller sensitivities.
Yeah.
And
Yeah, I
so
follow that. Yeah.
if we're looking at production in the same way,
Yeah.
the question is not what well, first the question is what's the sensitivity to production, but then the question is how much difference is there in production
Across different societies.
across societies, or you can do it internally, it's across age.
Yeah.
So in this case, the plots that I did of the fitness contribution multiply the sensitivity times the actual production.
Yeah.
So that's the effect of if you lost production at that age. If the production was less at that age, then you'd have a lower sensitivity or a lower
Okay.
effect, right?
Yeah, so my question, sorry, that's fantastic and very, very relevant to this issue. My question is, are you trying to build a model that accounts for the evolution of human life history from a chimp-like condition? Or are you trying to just model current selection pressures in existing hunter-gatherer ethnographic contemporary populations that might give you insight into
Right.
ongoing selection in the sort of Holocene portrait of human social economics?
Well, it's both. I mean, what we're doing is really a comparison of extant stuff.
Yeah.
So what is going on, but we also have, once we dial in this model a little, where the predictions are a little bit tighter, we're going to do exactly that, where we're looking at different skills, activities, different subsistence strategies, and we're going to compare chimpanzees that have a low skills subsistence strategy and humans that have a high skills intensive strategy, and we're going to look at what would be the conditions that would favor the advent of high skills activities.
Yeah.
So essentially, if you have old people around that have some skills and most people are not doing very high skilled activities, there's room to increase the skills level of activities and increase the complexity of subsistence, and that's the cumulative culture angle essentially. Any other questions?